origin of life. Very important. So listen till the very end. Okay? Let's start.
So, what if I told you that the origin of life on Earth wasn't, a biological event at all?
Right, which sounds completely counterintuitive.
Exactly. Like, what if instead of being some messy, unpredictable lottery ticket that somehow got cashed in by a lightning strike in a primordial puddle, what if life was just a mathematical equation solving itself?
It's a fascinating shift in perspective.
It really is.
Yep.
Today, we're entirely stripping away the biology. We're throwing out the idea of the lucky accident and looking at a stack of sources, specifically these groundbreaking statistical mechanics models by researchers Varanasi and Koranaga.
Yeah, and their work builds heavily on the framework of Kaufman networks.
Right, Kaufman networks. And these papers propose that life is actually a mathematical mandate, like a phase transition written into the very topological fabric of the universe.
Which is a huge claim.
Massive. So, okay, let's unpack this, because if you are a fan of deep math, percolation theory, and cosmological mysteries, we're going into maximum detail for you today on this deep dive.
We really are.
Our mission today is to pinpoint the exact quantifiable threshold where dead chemistry violently shifts into self-sustaining complexity.
Yeah, and to start, we really have to understand that we are analyzing a singularity in chemical space here.
Okay, a singularity.
Right. The models we are examining today, they don't describe a slow, Darwinian crawl from simple molecules to complex cells.
Which is what we all learned in high school, right? The gradual slope.
Exactly, the gradual slope. But these models describe a mathematical switch, a very precise state change, where a chaotic, disconnected system of molecules hits a critical density of interaction and then instantaneously reorganizes into a unified self-maintaining network.
That concept of a switch completely upends that traditional biology narrative. It's so sudden. And the sources center this entire phenomenon around something called an RAF set. That's RAFF.
Yes.
I really want to start at the foundational mathematics of this. What exactly is the topology of an RAF set?
So the acronym stands for reflexively autocatalytic and food generated.
Reflexively autocatalytic and food generated. Okay.
Yeah. Right. It basically represents the absolute minimum theoretical requirement for a chemical system to be considered self-sustaining.
Got it.
To understand the topology, we first isolate the autocatalytic component. In standard chemistry, you have catalysts, right?
Yeah, substances that lower the activation energy of a reaction without being consumed by it.
Exactly. Autocatalysis is simply a reaction whose product acts as a catalyst for that exact same reaction.
So it speeds itself up.
Yes, the system accelerates its own production. It's a localized feedback loop.
Okay, but an RAF set is reflexively autocatalytic. So what does the reflexively part add?
That's where we scale up from just a single localized loop to an entire network topology. The strict mathematical condition here is that every single reaction within the designated set, every single one, must be catalyzed by a molecule that is produced within that same set.
Oh, I see.
So molecule A catalyzes the formation B, and then B catalyzes C, and C catalyzes the formation of A.
It's like a closed circle.
Yeah, you establish a closed combinatorial loop where no reaction relies on an external specialized enzyme. The network essentially pulls itself up by its own catalytic bootstraps.
That makes total sense. So the community of molecules becomes entirely self-sufficient regarding its reaction speeds. But, they still need raw materials, right?
They do. And that brings in the F part, food generated.
Right.
The network needs a continuous influx of mass to keep going. The mathematical boundary condition dictates that every reactant entering the system has to either belong to a basic food set, which is just simple, environmentally available monomers, or it must be a product previously synthesized by the RAF network itself.
Okay, I picture this sort of like a self-building city.
Oh, that's a good analogy.
Like the food set is the raw timber and stone just scattered out in the forest, and the reflexively autocatalytic part represents the specialized labor in the city.
Right, exactly.
So the carpenter builds a reinforced forge for the blacksmith hammers out stronger trowels for the mason, and then the mason builds a protective workshop for the carpenter.
That's perfect.
They import the raw timber and stone, and through their mutually created tools, they construct this entirely self-sustaining infrastructure.
That is an excellent mapping of the topology. And, for decades following Stuart Kauffman's initial proposals regarding random Boolean networks back in the late 20th century, theoretical physicists really wondered about the probability of such an infrastructure forming spontaneously.
Because it sounds incredibly unlikely, just random chance doing that.
Exactly. But Varanasi and Koronaga's formalization translates that localized probability into a universal mathematical threshold. They take the immense complexity of a primordial soup and condense it down to a single equation governing the probability of catalysis.
And we promised the listeners maximum mathematical detail today, so let's walk through that actual formalization. How does the model calculate the probability of this chemical city spontaneously organizing?
So the core equation defines the variable P. And P is the probability that any randomly selected molecule in the system will catalyze any randomly selected reaction. The formula is simply P equals F divided by the cardinality of the set R.
Let's pause and clarify that for the listener. By cardinality, we are talking about the absolute size or number of elements in the set, correct? So it's the total number of possible reactions.
That is exactly correct. In a primordial chemical environment containing thousands of different monomer types, the combinatorial explosion means the cardinality of R is an astronomically large number.
Like mind-bogglingly big.
Yes. It represents every possible way every molecule could theoretically interact with every other molecule. And because that denominator, the cardinality of R, is so massive, the baseline probability P is infinitesimally small.
Which honestly makes sense. I mean, the chances of a random worker randomly finding the exact right tool for a specific task out of billions of possibilities is basically zero.
Which brings us to the numerator of the equation, the variable F.
Right.
This is a critical parameter. The variable F represents the expected number of catalyzations per molecule. It's essentially a measure of average connectivity.
Okay, so if you pick a molecule at random, how many reactions on average does it have the physical capacity to speed up?
Precisely. And the probability P is entirely bottlenecked by this value F. The Varanasi-Koronaka computational models isolate a highly specific behavior surrounding this parameter.
This is where we get to the switch, right?
Yes. The computational modeling reveals a profound non-linear phase transition. When the connectivity parameter F reaches a value of approximately 1.25.
Wait, 1.25 exactly?
Specifically within a narrow margin of plus or minus 0.1. But when it hits that threshold, the entire behavior of the mathematical space fractures.
Wow.
Below this threshold, the probability of an RAF set forming asymptotically approaches zero as the system scales. It's basically impossible. But above 1.25, the probability skyrockets to essentially 1.
It goes from 0 to 1 just like that.
Yes, the system undergoes a sudden, radical reorganization. Life switches on.
Okay, wait, I need to push back on this a little bit.
Yeah.
How can abstract mathematics dictate physical chemistry like that?
What do you mean?
Well, molecules floating in a hydrothermal vent, they don't know what a variable is. They don't know when their collective average connectivity hits 1.25. They are just blind atoms obeying localized electrostatic forces, right?
That's a great point. But the molecules don't need to know the math because the math is describing the overarching topology of their interactions, not their individual chemical properties.
So it's bigger than the chemistry.
Exactly. Think of it as a fundamental law of statistical physics that applies to any network, regardless of what the nodes are actually made of. The critical point of air being approximately 1.25 is universal.
Okay.
It remains invariant regardless of the size of the network, as long as the number of molecule types, let's call that n, is greater than or equal to 2. It's just a mathematical property, complex systems reaching critical density.
That is wild. That implies the origin of life isn't some freak biological accident unique to Earth's carbon chemistry at all.
Not at all.
It is a mathematical certainty built into the rules of networks. Like, if you gather enough building blocks and they have just enough potential interactions to push that F value past 1.25, they literally have no choice but to form an REF set.
Yes, and to really understand the physical mechanism forcing that transition, we have to look at percolation theory.
Percolation theory.
Yeah, it's a branch of statistical mechanics that studies the behavior of connected clusters within a random graph.
So walk us through the microscopic reality of the chemical soup as it approaches that threshold. What does percolation actually look like in real time?
Well, when your system is operating with an F parameter strictly less than 1.25, it exists in what we call a frozen phase.
Frozen phase.
The environment contains these tiny, isolated islands of catalytic activity.
Yeah.
So molecule A might catalyze B, forming a microscopic 2-cycle.
Okay.
But this cycle is topologically isolated from a separate 3-cycle occurring just micrometers away.
So you basically have isolated puddles of chemistry that can't communicate or share resources with each other.
Exactly.
Ah.
But as you increase the chemical concentration, or maybe increase the ambient temperature to raise the reaction rates, the F value begins to creep upward.
Right.
You were essentially dropping new random topological edges into your network graph. And for a long period, nothing macroscopic changes. The isolated puddles just grow slightly larger.
Yeah.
You're adding connections, but the system overall remains disconnected.
Until F approaches 1.25.
Right. At that exact critical density, positive feedback triggers a microscopic cascade. A single new connection, just one random catalytic reaction forming between previously isolated clusters, suddenly acts as a structural bridge.
Oh, wow.
And because those individual clusters were internally primed and already dense, bridging them instantly unlocks dozens of secondary and tertiary catalytic pathways.
It's a chain reaction, and the math refers to the result of this cascade as a giant component, right?
Yes, the giant component forms and immediately consumes the available graph. Those isolated puddles instantaneously link up to form a continuous ocean.
That's incredible.
The vast majority of the molecules in the system are suddenly swept up into this massive interconnected RAF web.
The sources delve heavily into the calculus of this suddenness, and I think it perfectly illustrates why this is a true phase transition rather than, a gradual evolution.
The mathematical elegance here is striking. It really is.
Yeah.
If we define a variable S as the proportional size of our giant component, so the fraction of the system that is now living chemistry, essentially, we can analyze how it changes with respect to our connectivity parameter F.
We do that by looking at the derivative.
Exactly. We look at the derivative ds over df.
So as F approaches the critical threshold, which we'll call F sub c, the model shows that the derivative ds over df approaches infinity.
Yes, and for any of our listeners familiar with statistical mechanics, an infinite derivative at a phase boundary represents a topological singularity.
Let's break down what an infinite rate of change actually means here. It means that an infinitesimally small increase in the chemical concentration, like a change so microscopic it borders on the Planck limit, results in a massive finite change in the macroscopic connectivity of the system.
Exactly. On a phase diagram, the curve runs completely flat, representing the frozen phase, and then upon hitting F sub c, it just pitches into a vertical wall.
The sources use several physics analogies to ground the singularity, and one that really stands out to me is water breaking through a porous stone.
Oh, that's a great one.
You have a block of pumice, you apply water pressure to one side, and you slowly increase the pressure, driving water into the microscopic disconnected pores. For a long time, the other side of the stone remains bone dry.
Because the water is trapped in isolated pockets.
Exactly. But at a highly specific critical density of saturated pores, one final microscopic barrier gives way, bridging the pockets, and the water violently rushes through the entire stone all at once.
Another classic application of percolation theory is the sudden magnetization of ferromagnetic materials.
Okay, how does that one work?
So you cool down a piece of iron. While it is hot, the atomic spins are completely chaotic, pointing in random directions. The net magnetic field is zero.
Right.
As you cool it, local clusters of aligned spins start to form, but they remain isolated. The moment the material crosses the Curie temperature, an infinite derivative occurs in the alignment scaling.
And instantly, all the spin.
Yes, the metal becomes magnetic all at once.
We see the exact same mathematical architecture in epidemiology, too.
Oh, absolutely.
Like a virus hops between hosts. The transmission rate, the R naught, functions conceptually similar to our F value. You have isolated outbreaks in different cities. As long as R naught remains below a critical threshold, the outbreaks just burn out.
But the moment the transmission rate crosses the critical boundary,
it ceases to be a collection of isolated events. It instantaneously scales into a globally connected web of transmission, a pandemic.
And whether we are discussing fluid dynamics in porous media, the quantum spins of a ferromagnet, the transmission vectors of a pathogen, or the chemical origins of life, we are observing the exact same underlying mechanism.
Emergence.
Yes, emergence.
And emergence implies that the defining characteristic of the system isn't actually found in its constituent parts. Like, no single carbon atom or water molecule possesses the property of life.
That's the beauty of it.
Yeah.
The phase transition is a strictly topological property of network.
Right.
When you reach a sufficient density of connections, macroscopic properties emerge that are fundamentally impossible to predict, but just reducing the system down to its individual nodes.
So the mathematical architecture of the whole dictates the behavior of the parts.
Exactly. You look at a single H2O molecule, and the concept of wetness simply doesn't exist.
Right.
Wetness is an emergent property requiring billions of molecules interacting at specific densities and temperatures. Life is just the ultimate iteration of wetness. It's an emergent property of chemical topology.
Which brings us to a massive structural hurdle in this whole theory.
Right. We have this really robust, mathematically elegant theory. We have the calculus demonstrating a topological singularity at F is approximately 1.25. But abstract graphs in a computer simulation don't suffer from thermodynamic decay or side reactions.
Yeah, no, they don't.
So can this mathematical switch actually be built in a physical laboratory?
That's the big question. The sources spend a lot of time on the experimental reality. And it seems like we have gotten tantalizingly close to proving the math, but researchers keep hitting a wall regarding how they set up the initial conditions.
The 2009 experiment by Joyce and Lincoln is a perfect example of this.
Yeah, the Joyce and Lincoln study was a watershed moment for sure. They successfully engineered an artificial RAF set utilizing cross-catalyzing RNA enzymes, which are known as ribozymes.
Okay.
They synthesized two specific ribozymes, E1 and E2. The structure of E1 allowed it to act as a catalyst, seamlessly assembling E2 from smaller, free-floating RNA oligonucleotide fragments in the solution.
Right.
And conversely, E2 acted as the specific catalyst required to assemble E1 from its respective fragments. So they built a perfect, isolated two-cycle, reflexive autocatalysis right there in a test tube. E1 builds E2, and E2 turns around and builds E1. I mean, that physically proves that mutual autocatalysis is chemically viable.
It does. It proves the chemical mechanics work perfectly. The critical flaw, however, lies in the methodology, especially if we are attempting to utilize this experiment as proof for the spontaneous de novo origin of life.
Because they kind of cheated, right?
Well, the Joyce and Lincoln system relied entirely on intelligent design.
Right. The researchers didn't just pour a random slurry of nucleotides into a beaker and wait for percolation to drive the value up. They used incredibly advanced biotechnology to highly specifically sequence and match the RNA strands.
Exactly. So they would fold into the exact 3D conformations required to catalyze each other.
It was an exercise in rational design by top-tier biochemists. But to empirically validate the Varanasi-Koranaga mathematical model, we must observe an RAF set emerge spontaneously from a random, uncurated library of monomers without a human observer guiding the thermodynamics or, manually selecting the sequences.
Right. But we do have historical precedents for spontaneous chemical networks. The sources bring up the foremost reaction, which actually dates all the way back to Alexander Butlerov in 1861.
Oh, wow, that old.
Yeah. The foremost reaction is a brilliant, entirely natural chemical analog. If you take simple formaldehyde, which is a basic, highly reactive carbon molecule, and you place it in a basic solution with a divalent metal catalyst like calcium, it begins to polymerize.
Okay.
It forms this wildly complex mixture of higher sugars, including ribose.
Right.
And the fascinating topological feature of the foremost reaction is that the intermediate products, the sugars themselves, act as catalysts to drastically accelerate the consumption of the remaining formaldehyde.
Oh, so the network naturally fuels its own expansion.
Yes, it is one of the oldest and most robust examples of spontaneous autocatalytic networks. It requires no human engineering whatsoever.
But there's a catch, isn't there?
There is. While it is a powerful metabolic engine, it lacks informational complexity. It generates a chaotic smear of sugars, but possesses absolutely no mechanism for genetic memory or sequence specificity.
So if we can't cheat by pre-programming RNA sequences in a lab, and simple sugar networks don't contain enough information, how does a natural environment force random amino acids or nucleotides past that critical 1.25 threshold?
It's a huge problem.
Because the math requires a massive, sustained spike in concentration to trigger percolation, but the early Earth didn't exactly have researchers carefully managing molarity in glass beakers.
No, but the Earth utilized geology as its centrifuge.
Geology.
This is heavily explored in the research coming out of Jack Szostak's laboratory, focused on the mechanics of the prebiotic kitchen, specifically wet-dry cycles in geothermal fields.
Okay, paint a picture of the physical mechanics of a wet-dry cycle for us. How does a hot spring manipulate the phi variable?
Well, consider a geothermal geyser or a hydrothermal pool. The water contains a highly dilute mixture of simple trace monomers. This is our food set. The geyser erupts, or the pool surges, splashing this dilute water onto the surrounding heated rock surfaces. This initiates the dry phase.
Okay.
As the water evaporates the hot rock, the dissolved molecules are left behind. They are mechanically forced into closer and closer proximity. the spatial volume decreases, which causes the chemical concentration to just skyrocket.
And as the physical distance between the molecules shrinks, the probability of them interacting, the value, naturally climbs.
Exactly. Without any biological enzymes at all, the sheer thermodynamic pressure of the evaporation forces the monomers to undergo condensation reactions, linking together to form short, random polymer chains.
Wow.
Then the environment shifts. The geyser erupts again, or it rains. This is the wet phase.
Okay, so what happens then?
The newly formed polymers are washed back into the bulk aqueous pool.
Where they are free to mix, fold into complex three-dimensional structures, and randomly interact with different chains.
Right, and the cycle then repeats. Wet, dry, wet, dry. Millions of iterations over geological timescales.
So the environment itself is doing the heavy lifting.
Yes. The dry phase acts as a mechanical pump, continuously driving the concentration and the network connectivity up toward the F equals 1.25 percolation threshold, forging new combinatorial bonds and testing random topological arrangements.
So if researchers try to replicate this exact geological pump in a laboratory setting today, tossing random monomers through simulated wet-dry cycles, what exactly are they looking for?
Well, they need to know they've succeeded.
Right. How do they definitively prove that the mathematical switch has flipped, rather than just observing a chaotic chemical sludge?
The models actually establish a rigorous 5-point set of experimental criteria.
5 criteria.
Yes. Any laboratory attempting to claim the spontaneous synthesis of an RAF set must unequivocally satisfy all 5 constraints.
Okay, let's go through them.
The first metric they monitor is the kinetic growth curve. They're looking for sigmoidal growth.
Meaning an S-shaped curve on the graph rather than just a straight line.
Exactly. In standard unlinked chemistry, the accumulation of a product over time generally follows a linear trajectory, or perhaps a simple logarithmic decay as reactants are consumed. It's a steady, predictable rate.
Right.
But if an autocatalytic network spontaneously emerges from the mixture, the kinetics violently shift. The products begin catalyzing their own formation.
Oh, I see.
The growth curve remains flat during the frozen phase, then sharply inflects upward in an exponential explosion of product generation before finally leveling off as the environment's food supply is saturated.
And that sigmoidal shape is the unmistakable thermodynamic footprint of an autocatalytic cascade.
Precisely. But just observing an explosion in reaction rate isn't enough to prove the specific topology of an REF set.
Right, because an S-curve just proves something is speeding up. How do researchers prove that the reactions form those required closed loops?
That requires diving into the system with high-resolution mass spectrometry. They must physically map the chemical pathways.
So they have to trace it atom by atom, essentially.
Yes. They have to trace the isotopic signatures to prove that the catalyst driving the formation of molecule A is indeed produced downstream by molecule C, completing the reflexive loop.
Which proves the network is functionally closed. But what about structural integrity? The math of percolation suggests that once a giant component forms, it is highly resilient because of the sheer density of interconnected pathways.
And this brings us to the third criterion, robustness. The mathematical models predict that a fully formed RAF network possesses intense topological redundancy.
How redundant are we talking?
The simulations indicate that you can systematically target and delete an average of 9 random catalytic links from the network, and the overarching structure will simply reroute and survive.
You can effectively sever the internal supply lines of the chemical city 9 separate times, and it just routes around the damage. That's incredible. How do you test that mathematical redundancy physically in a lab?
Through brutal dilution protocols. Experimenters take a thriving, concentrated chemical network and suddenly dilute the solution by a factor of 10 or more.
Just flood it with water.
Right. They flood the system, massively dropping the concentration and breaking countless weak intermolecular interactions. If the mathematical theory of the giant component holds true, the network should not collapse.
The core loops survive.
Yes, the core topological loops should endure the shock and slowly rebuild the concentration of the system.
Okay, so that tests the autocatalysis and the robustness. The fourth criterion tests the food-generated aspect, right?
Yes. The researchers have to systematically starve the network. They remove the simple base monomers from the input stream.
And what happens?
Well, if the network is truly pulling its raw materials from the environment rather than just slowly degrading a finite internal stockpile, removing the food set should cause the entire system to instantly crash.
It confirms the network is an open thermodynamic system reliant on environmental flux. Okay, so satisfying those 4 criteria proves you have successfully created a chemical RAF set.
But to bridge the gap to actual biology, you must cross the final monumental hurdle, The fifth criterion is inheritance.
Inheritance. So the system must possess the ability to not just maintain its current physical mass, but to pass its specific topological structure to a new generation.
Exactly. If a highly efficient chemical subnetwork emerges in one pool, can it seed an adjacent pool with its exact organizational recipe?
And this is where the experimental models hit a massive, seemingly insurmountable mathematical wall.
They really do.
Because attempting to pass on that structural information introduces the parasite problem.
Yes. The parasite problem, which the sources note was heavily modeled and quantified by Paul Higgs in 2015. It represents the ultimate paradox of probiotic chemistry.
Right. The very mathematical principles that allow the network to form also guarantee the emergence of its destroyer.
It's tragic in a way. Imagine our interconnected chemical city operating at peak efficiency. The RAF set is humming, generating a rich surplus of catalysts and raw materials.
Sounds great.
But in this open, highly reactive soup, random side reactions are ineffable. Eventually, a new molecular sequence forms, and this sequence is a structural parasite.
What makes it a parasite?
Its conformation allows it to readily accept the catalytic assistance of the network. So it utilizes the shared tools to copy itself at an astonishing rate. But it provides zero catalytic feedback. It gives nothing back to the system.
It is a purely selfish node in the graph. It consumes the environmental food set, it drains the catalysts, and it exponentially replicates.
And the mathematics of resource competition are brutal here. Because the parasite expends zero thermodynamic energy catalyzing other reactions, it replicates significantly faster than the cooperative molecules.
So it just takes over.
Completely. In an open primordial soup, the mathematical models show the parasites will inevitably arise, outcompete the RAF network resources, and trigger a catastrophic collapse of the entire system. The city basically starves itself to death, feeding the parasite.
Which poses a massive existential question. If the equations dictate that open chemical networks will always be consumed by mathematical parasites, why are we sitting here having this conversation?
Right, how are we alive?
How did early life survive its own mathematics?
To circumvent the parasite problem and transition from a fragile chemical web to enduring biological evolution, the system cannot simply rely on a single phase transition. The math dictates that it requires a precise sequence of structural shifts, a cascade.
And this is where the sources introduce an absolutely stunning piece of conceptual synthesis. They map this rigorous cascade of statistical phase transitions onto ancient Slavic mythology.
It's a beautiful metaphor.
They referred to this sequence as the 5 touches of Mokosh.
Right. In the ancient Slavic pantheon, Mokosh is the supreme goddess of fate. But functionally, she's the deity of weaving, spinning, and the entwining of threads. She takes raw, chaotic fleece and forces it into a structured, unified line.
The metaphor perfectly mirrors the behavior of Kaufman networks. The chaotic primordial soup is the raw fleece. The geological wet-dry cycles provide the spinning wheel's mechanical pressure.
And the resulting thread is the RAF set chaotic molecules suddenly woven together into a unified topological structure at critical density.
The authors break down the origin of life into 5 hierarchical thresholds, 5 mythological interventions. And the sequence is rigid, right?
Very rigid. No step can occur unless the mathematical boundary conditions of the previous step have been entirely fulfilled.
We've actually spent the first half of this deep dive covering the first touch, the finger of Mokosh itself.
Yes, the first touch is percolation. Mathematically, it is the exact moment the connectivity parameter F reaches 1.25. It is the spontaneous weaving of the chemical thread, the emergence of the RAF network from the frozen phase.
But as Higgs's models proved, a naked thread floating in the ocean will just be devoured by parasites. The thread needs armor. It needs the second touch.
The second touch is titled the Breath of Velas. In the mythology, Velas is a multifaceted god associated with the earth, waters, and the underworld.
Okay.
But most importantly for our models, he is the god of boundaries and physical thresholds, the division of spaces.
So what is the biological equivalent of Velas breathing a boundary into existence?
Compartmentalization, the spontaneous thermodynamic assembly of lipid vesicles. We call them protocells.
Fatty acid bubbles forming in the turbulent water.
Exactly. Amphiphilic molecules, which have a water-loving head and a water-hating tail, will automatically self-assemble into hollow, spherical bilayers when agitated in water.
Oh, so it just happens naturally.
Yes, it is a purely physical, thermodynamic imperative to minimize energy. If a delicate RAF network happens to be enclosed within one of these forming vesicles, it's instantaneously partitioned off from the bulk ocean.
The chemical city builds a wall, And mathematically, why does this isolation solve the parasite problem?
It shifts the mathematics of survival from individual molecule competition to group selection.
How so?
If a parasite spontaneously forms inside a specific protocell, it will rapidly consume the resources inside that bubble. That specific vesicle will die.
Right.
But the thousands of other protocells in the surrounding environment, the ones that did not generate a parasite, remain untouched. They continue to metabolize, grow, and mechanically divide.
Oh, wow. So the physical boundary of the membrane localizes the parasite infection, basically sacrificing individual cells to preserve the overarching chemical lineage.
Yes. Volas breathes a physical body around the math. But a protected chemical engine still lacks a blueprint. It can grow and divide, but it can't pass on complex, high-fidelity instructions to its offspring. It needs memory.
Which requires the third touch, the Eye of Sarog. Svarog is the celestial blacksmith, the god of fire and the sun. The eye represents illumination, reflection, and the precise copying of form.
This represents the transition to true genetics, the emergence of templating molecules like RNA. But there is a terrifying mathematical bottleneck here, known as Eigen's error threshold.
We're done for Eigen, right?
Yes, a physical chemist who won the Nobel Prize. He mathematically formalized the limits of genetic replication.
Okay, walk us through it.
If a protocell relies on a genetic code, it must replicate that code when it divides. But early replication mechanisms, lacking the advanced proofreading enzymes of modern DNA, were incredibly sloppy. Mutations and copying errors were rampant.
And if you accumulate too many errors, the blueprint becomes completely unreadable.
Exactly. Eigen's equations demonstrate that there is a strict physical limit to how much information a system can hold based on its error rate. If the mutation rate exceeds this threshold, the system undergoes an error catastrophe.
An error catastrophe.
Yes. The genetic information literally dissolves into topological noise over a few generations.
So what's the formula for this limit?
The mathematical boundary is unforgiving. The copying accuracy per monomer must be strictly greater than 1 minus 1 divided by the square root of n, where n is the total length of the sequence.
Let's run those numbers to show the listener how thin this margin really is. So if our protocell develops a highly useful RNA strand that is 100 molecular letters long, n is 100.
Right.
The square root of 100 is 10. 1 divided by 10 is 0.1. So the formula requires an accuracy strictly greater than 1 minus 0.1.
Which is 0.9, or 90%.
So for a mere 100-letter sequence, these blind, primitive molecules floating inside a fat bubble must invent a chemical copying mechanism that physically matches the correct nucleotide with at least 90% accuracy every single time.
And if they hit 89%.
The math dictates that their genetic lineage melts into chaos.
Exactly. The Eye of Svarog represents the system successfully developing the chemical mechanics to cross Eigen's threshold. Once the protocell achieves high-fidelity replication of its internal state, the foundation for history is laid.
Which unlocks the fourth touch.
Right.
The wisdom of Rod. In Slavic mythology, Rod is the primordial creator, the supreme god of ancestry, kinship, and the generation of lineages.
The wisdom of Rod is the Darwinian transition. The system now possesses all three mandatory prerequisites for evolution.
And those are?
It has heredity, provided by the high-fidelity RNA templates. It possesses variability, generated by the mutations that still occur just below Eigen's error threshold. And it is subject to selection, as the localized protocells actively compete for the finite resources of the environmental food set.
This is the moment the system stops being a purely cyclic chemical engine and shifts into directed, exponential biological optimization.
Yes.
The network gains the ability to remember structural variations that increase efficiency and ruthlessly discard those that don't. It is the literal birth of the evolutionary algorithm.
It is a profound shift in complexity. However, a walled city with a perfect blueprint and generations of optimized workers still faces a fundamental limitation.
What's that?
It remains a passive entity, entirely dependent on whatever ambient thermal or chemical energy happens to drift across its membrane. To become a truly autonomous biological organism, it requires a dedicated power plant.
The fifth and final touch. The thunder of Perun. Perun is the highest god of the pantheon, the lord of thunder, lightning, storms, and unbridled active energy.
The thunder of Perun is the metabolic transition, specifically the evolution of a mechanism known as chemiosmosis.
Chemiosmosis.
To break free from environmental energy constraints, the cell must learn to generate and harvest its own electricity.
Now, when we say generate electricity at the cellular level, we obviously aren't talking about sparks flying around. We are talking about the manipulation of subatomic particles across a physical barrier, How does chemiosmosis physically function?
The cell utilizes the energy from its chemical reactions to actively pump protons, which are positively charged hydrogen ions, out of its interior, pushing them across the lipid membrane into the outside environment.
Okay.
Because the membrane is largely impermeable to these ions, they become trapped on the outside.
This creates a massive imbalance, a proton gradient.
Exactly. You have a high concentration of positive charge on the outside of the membrane and a relative negative charge on the inside. The cell is basically constructed a microscopic electrochemical battery.
And the thermodynamics of the universe demand that this imbalance be resolved, right? Like the protons violently want to flow back inside to equalize the charge.
And the cell weaponizes that desire.
Oh.
It installs highly specialized transmembrane proteins called ATP syntheses. These are literal molecular turbines.
Turbines, like a dam.
Exactly like a hydroelectric dam. The cell opens these channels, allowing the protons to flood back inside. The physical kinetic force of the rushing protons mechanically spins the rotor of the ATP synthase protein.
It literally spins.
It physically spins. And this rotational energy is used to jam a phosphate group onto an ADP molecule, creating ATP adenosine triphosphate.
The universal energy currency of all life on Earth.
It is an engine of staggering mechanical beauty. Once the cell masters chemiosmosis, it achieves complete energetic autonomy. It no longer waits for a random geological event to provide energy. It actively maintains its own internal electrical storm. It is the lightning.
Taking a step back and looking at the architecture of this theory, it is just breathtaking.
It really puts things in perspective.
You begin with the first touch, the pure mathematics of percolation weaving a network. Valis builds a protective wall around it. Svarog grants it high-fidelity memory by beating the physics of error catastrophe. Rod initiates the algorithm of Darwinian evolution, and Perun strikes the system with autonomous electrical power.
It takes 5 distinct, unforgiving mathematical phase transitions to make the journey from dead primordial puddle to a living, metabolizing cell.
And the implications of these 5 thresholds extend far beyond our own planet.
There you do.
If we apply this rigorous mathematical framework to the cosmos at large, it forces us to fundamentally rewrite the rules of astrobiology.
Which leads us into the final section of our deep dive, cosmological implications. If the physics of percolation and the mathematics of the 5 touches are universal laws, how does that change where we look for life in the universe?
The classic approach has always been centered on the habitable zone.
Right. Historically, the habitable zone, the so-called Goldilocks zone, has been defined almost exclusively by stellar radiation.
It is the specific orbital band around a star where the ambient temperature is suitable for liquid water to pool on a rocky surface. Earth sits right in the middle. Venus is too close, so its oceans boiled away. Mars is too far, so its water froze solid.
But the Varanasi-Coronaga models, coupled with Solstak's research into the prebiotic kitchen, suggest that a stagnant puddle of lukewarm water is chemically useless.
A static pool will never trigger the first touch.
Never. The mathematical requirement for life is not simply the presence of a solvent. The absolute requirement is an environmental mechanism capable of driving the chemical concentration up to force the connectivity parameter F past 1.25.
You require an active geological or atmospheric engine.
You need the cosmic spinning wheel of Mokosh.
Wow. Therefore, the true habitable zone is dictated by thermodynamics and physical cyclability, not just orbital distance. This realization radically expands our search parameters.
It completely changes the game.
We are no longer limited to looking for Earth twins with calm surface oceans. We're looking for chaotic environments that support aggressive cyclical concentration.
That points our telescopes toward wildly inhospitable places.
Yeah.
Like Venus.
Venus! The surface of Venus is a literal hellscape that melts lead.
The surface is yes, but the atmosphere is a different story. The cloud decks of Venus exhibit massive convection currents.
Oh, I see.
Aerosol droplets containing complex chemistry are constantly swept up to the freezing upper atmosphere and then plunge back down toward the boiling lower layers. These violent vertical cycles could theoretically provide the massive thermodynamic concentration necessary to trigger an RAF network within the droplets themselves.
Wet-dry cycles in the sky. And it also points us to the outer solar system, to the ice moons.
Moons like Europa Orbiter or Enceladus around Saturn, they possess global subsurface oceans locked beneath miles of ice.
Right.
While the surface is frozen, gravitational tidal heating flexes the core of the moons, likely generating massive hydrothermal vent systems on the pitch-black sea floor.
The exact same prebiotic kitchens we think birthed life on Earth, The violent mixing of superheated, mineral-rich vent water with the freezing ocean provides the extreme thermal and chemical gradients required to mechanically pump the value.
The environments capable of triggering the first touch might be surprisingly common.
Which immediately forces us to confront a terrifying cosmological paradox.
The Fermi paradox.
Yes. If the universe is roughly 13.8 billion years old and contains trillions of galaxies, each with billions of stars, and if the first step of life-reaching foe is approximately 1.25, is a mathematical inevitability in any system with basic carbon chemistry and geological cycles, why is the cosmos so deafeningly quiet?
Where are the galactic empires?
Exactly. Where is everybody?
The mathematics of the five touches provides one of the most elegant and arguably chilling solutions to the Fermi paradox. It introduces the concept of the great cosmic filter.
A filter implies a barrier that almost nothing can pass through.
Right. We have established that reaching step one, the spontaneous formation of an RAF network via percolation, is mathematically highly probable given the right geological pump.
So the universe might very well be teeming with chemical life. Every hydrothermal vent on every ice moon in the galaxy might be spinning out chemical threads.
But remember, the rigidity of the cascade. To evolve into an organism capable of building radio telescopes and launching spacecraft, a system must survive all five thresholds.
Oh man.
What if the great filter isn't the origin of life, but the subsequent mathematical bottlenecks?
That changes the entire calculation.
Step one is easy, but what if step two, a chemical network randomly finding itself enclosed in a lipid vesicle before being annihilated by mathematical parasites, is a 1 in a billion alignment of probabilities?
And what if step 3 is even worse?
Yeah.
Step 3 is Eigen's error threshold, the mathematical mandate that you must achieve 90% copying fidelity for a 100-letter sequence without the aid of advanced enzymes.
The physics of error catastrophe are unyielding. It is entirely plausible that billions of worlds harbor oceans full of protocells that constantly hit Eigen's limit, their genetic codes dissolving into static noise before they can ever evolve.
They are just trapped in a perpetual loop of biological amnesia.
So we could be living in a universe that is absolutely overflowing with life, but is entirely stuck at the level of blind chemical bubbles.
Trillions of planets are weaving the threads of Mokosh, maybe even building the walls of Velas, but they fail to pass the mathematical trials of Svarog and Rod. They never build the metropolis.
The sheer statistical improbability of successfully navigating all five sequential mathematical bottlenecks suggests that while the initial spark of life is complex, autonomous biology is a macroscopic anomaly.
We survived a gauntlet that destroys 99.99% of all chemical networks in the universe.
That reframes our existence completely. We aren't just lucky, we are the statistical survivors of an impossibly strict mathematical labyrinth.
And understanding that labyrinth gives modern space exploration a highly specific target. We aren't looking for little green men anymore. The search parameters have completely shifted.
Look at the instrumentation on our most advanced interplanetary missions.
Like the Mars Perseverance rover.
Yes, currently analyzing the ancient delta deposits in Jezero Crater and the upcoming Europa Clipper mission. They aren't carrying equipment designed to detect complex biological organisms.
They are looking for the topology of the first and second touches.
Precisely. They're employing advanced spectroscopy and mass spectrometry to scan rock cores and ice plumes for the topological signatures of autocatalysis. They're hunting for anomalous, nonlinear concentrations of complex polymers that would indicate a historical runaway value.
They are searching for fossilized lipid formations, the petrified breath of Velas.
They're looking for the exact threshold where dead chemistry triggered an infinite derivative. They want to know if the geysers of Enceladus or the ancient lakes of Mars ever pushed a chemical network past F equals 1.25.
And if they find it, if we discover definitive evidence of a completely independent origin of an RAF set on another celestial body,
it will empirically validate the Varanasi-Coranaga models. It will prove once and for all that the emergence of life is a universal mathematical law of complex networks, not a localized earthly anomaly.
It would fundamentally alter humanity's relationship with the universe. We have covered immense ground today, moving from abstract equations to the depths of space. We began by discarding the notion of life as a chaotic biological accident.
We replaced the dice roll with the precise statistical law, P equals F divided by the cardinality of R. We observed that when the connectivity parameter F reaches roughly 1.25, the mathematics of percolation dictate a sudden infinite derivative in the system's connectivity.
The frozen phase instantaneously shatters, and isolated chemical reactions link into a massive, self-sustaining giant component.
We analyzed how the mechanical pressure of geological wet-dry cycles acted as a prebiotic pump, driving concentrations up to force that critical threshold.
We explored the immense difficulty of proving this transition in a laboratory without relying on intelligent design, navigating the strict physical requirements of sigmoidal kinetics, closed isotopic loops, robustness against extreme dilution, and environmental food dependence.
Which brought us face to face with the parasite problem, revealing that survival required a highly specific cascade of phase transitions, the 5 touches of Mokosh.
Percolation weaving the initial network. The thermodynamics of lipid compartmentalization building physical boundaries to isolate parasites. The brutal physics of Eigen's error threshold demanding high-fidelity memory. The onset of Darwinian selection driving true evolution. And the molecular turbines of chemiosmosis granting the system autonomous electrical power.
Finally, we applied these mathematical laws to the cosmos, expanding the habitable zone to any environment capable of cyclical thermodynamic pumping, while simultaneously confronting the chilling reality that the sequential strictness of these 5 thresholds likely forms the great cosmic filter.
It fundamentally changes how you perceive the world around you.
It really does.
The next time you look at a forest or a glass of water, or even your own hands, realize that the very fact you exist to observe them is the direct result of countless microscopic molecules crossing exact, unforgiving mathematical boundaries billions of years ago. You are the emergent property of a topological singularity.
Which leads me to one final, perhaps unsettling speculation that extends directly from the mathematics we've discussed today.
Oh, lay it on us.
We have established mathematically that biological life is not a distinct substance, but an emergent property. It is a phase transition that predictably occurs when a chemical network becomes sufficiently dense and complex.
Right.
The macroscopic behavior of the whole emerges from the topology of the parts, entirely independent of the individual nodes.
The whole is mathematically greater than the sum.
Therefore, if the transition from dead chemistry to living biology is simply an inevitable topological phase transition triggered by network density, what are the mathematical implications for a biological neural network, like the human brain?
Oh, right.
But consciousness itself, the very self-awareness allowing us to process these mathematical concepts, simply be the 6th touch of Mokosh.
Oh, wow.
If life is just a chemical network hitting an F value of 1.25, is consciousness just another inevitable mathematical phase transition waiting to switch on whenever a biological network of neurons hits its own critical density of connections?
That implies our minds are biological, exact same percolation equation playing out at a higher fractal level, an infinite derivative of thought.
It is the ultimate manifestation of emergence. We are the universe's mathematics, finally becoming dense enough to calculate itself.
That is a concept that is going to keep me up for a long time.
Me too.
And with that mind-bending realization, we are going to wrap up today's deep dive into the statistical mechanics of life. We hope we've given you a profoundly new lens through which to view your origins, the cosmos, and the mathematical machinery operating inside your own mind. Keep looking at the world, keep questioning the mechanics of reality, and never stop wondering about the invisible laws that govern it all. Take care. What if I told you that the jagged edge of the cloud floating outside your window right now isn't actually a 3-dimensional object? Like, what if that cloud, with all its chaotic bumps and wisps,